The first part of Lab 6 makes reference to anatomy and physiology stuff that you've had before, but is very important. The glottal cycle, which ideally y'all would be able to give a description of off the top of your head to somebody who is interested in how the sound of the voice is made. Alright, rather than write one out like that, I wrote one out with mistakes in it to be corrected. So we start with expiration, which I don't have in here, whether you want to add that on the front or not. You know, depends on how picky you want to be. But it does start with expiration. Then we bring the vocal folds together, but that is adducting, not abducting, by our interarytenoid and lateral cricoarytenoid muscles. So vocal folds are temporarily held shut, but not by air pressure in the oral cavity. We could probably just scratch that and leave it, because it is true that they're temporarily held shut by that muscular activity. Air pressure does build in the trachea beneath the vocal folds due to lung compression. That's part of that expiration that's happening. When that air pressure builds sufficiently, the vocal folds are pushed open. That is also true. After the release of air pressure, elastic forces try to return the vocal folds to their original, once again, adducted state. However, the moving airstream past the vocal folds creates an increase in air pressure that slows the return of the vocal folds to the closed position, the Bernoulli effect. Kind of like the abducted-adducted thing I have in there. That's backwards. That moving airstream creates a decrease in the air pressure. And that decrease in the air pressure then speeds the return of the vocal folds back together, because it's pressure that's holding them apart. So the lower that pressure is, the quicker they'll return to being together. That is the Bernoulli effect. And I guess if I was being picky, you wouldn't use however as a transition word there. You'd say something like in addition maybe, but that doesn't have anything to do with the glottal cycle. And phonation ceases when the vocal folds are adducted. No, again, I've got that in the backwards position, which is an easy mistake to make. Phonation ceases when you abduct, and then, expiration stops as well at some point, though you might be switching from a voiced sound with phonation to a voiceless sound without phonation, so you might have expiration continue as you move on to other kinds of speech sounds. Alright, so review that glottal cycle. Important. Rest of the lab gets into some of the new material that you haven't seen before on the acoustics of the voice. First two questions actually is kind of our idealized view of what phonation looks like if we could make an acoustic recording of it without the rest of the head getting involved and that sort of thing. And like any other sound, our two main measures of that are frequency and amplitude. In the case of phonation, we have that basic vibration of the vocal folds that creates a fundamental frequency for that complex periodic sound, its lowest frequency. But then that phonation sound is a special class of sounds, a harmonic series, where in addition to that base frequency, we've got all of its multiples. Those multiples are called harmonics. Labeled from the first one would be twice the fundamental frequency, second one up by another 150, third one up by another 150. I guess I could put 150 in each step, and so forth. Up another 150 gets us to 750, 900, 1050, and 1200. Now, in terms of the amplitude, if the phonation starts at 70 dB, that amplitude drops off, kind of like it does in this graph down here, where the amplitude gets lower as we go higher in harmonics. The default, if I don't say something else more specific about what happens with the amplitude, the average, the typical, typical is maybe a better word, is for that to drop by 12 dB per octave, which is a doubling of frequency. So when we go from the fundamental of 150 to the first harmonic, we do indeed double the frequency. So we would drop that amplitude by 12, which is get us down to 58 dB. That's 70 minus 12. Now, the next doubling of the frequency happens as we go from the first harmonic to the third harmonic. So the frequencies increase linearly in terms of mathematics, add the same amount each time. For the amplitudes, it decreases each time we double. So when we get up to that 603rd harmonic, we would have 12 fewer, so 46 dB, which would be that 58 minus 12. And then our next doubling takes us all the way down to the 7th harmonic. So we would drop another 12, which takes us down to 34 dB. That 46 minus 12. Okay, so that kind of lays things out as I talked about them in class, but in sort of a table form, so you can see the range of information that we have, where I've got X's in some of these amplitude columns for things where we're not going to worry about computing that. There is an amplitude value somewhere in between the values that we can compute that are involved with octave doublings of our frequencies. All right. Next we have a comb spectrum, a sort of idealized spectrum with each of the frequency components as a perfectly sharp stick without any noise in it, representing phonation. In this particular case, I have this up to 2000 hertz, as I often do, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 ticks in there. So each one of those, if that's 1000, should be 100 hertz. If there was some other number of sticks, well, take 1000, divide it by that number of sticks, and you would get what that fundamental frequency is, roughly, if you're looking at a comb spectrum. For the harmonic roll-off, my first stick here is my fundamental frequency, F0. My second stick here is my first harmonic, H1. And the roll-off would be, well, how much does that amplitude drop? Looks like it goes from 80 down to 60, so we've subtracted off 20. Now, since this is a fancy, perfect theoretical comb spectrum, we could stop there, but kind of previewing what's on the second page of this exercise, my next drop would be to go from the first harmonic down to the third harmonic, which is over here. Fundamental 100, first harmonic 200, third harmonic 400, a doubling, an octave increase. So for the amplitude part of the problem, we're skipping a harmonic there. That takes us from 60 down to 40. So again, dropped by 20. Next harmonic we would look at would be 4, 5, 6, 7, which would get us from 400 down to 800. Or sorry, 400 up to 800, I guess I should say. Next doubling of the frequency at the 7th harmonic, just like up on my chart here. And once again, from 40 down to 20, because I mathematically constructed this. We have dropped by 20, so we got a 20 dB per octave roll-off. That is a steeper roll off than we have typically. It's a bigger negative number. All right, second page has a couple of similar problems to that theoretical comb spectrum problem, but a couple of extra wrinkles to it. One is that I took a recording of myself producing a steady state vowel, did some fancy filtering to it to try to reconstruct and get back to just the phonation part of that speech signal, and so I get something like this. So here's my fundamental frequency, sorry, F0, man. My first harmonic is here, second harmonic, third harmonic, fourth harmonic, fifth harmonic, so you can see this isn't quite as perfectly regular, sixth and seventh harmonic. All right, I could hold up a piece of paper to this to see what it looks like if I'm straight up and down. I can do my insert a stick trick, try to start at this point and go straight vertical. That looks not too bad. I may be a smidge off to the right, but I'm going to say, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 again. I'm going to say it looks like I'm right around 200 hertz then for that fundamental. First harmonic then would be around 400 if I move this stick over. Actually, that didn't look that close to 400, so maybe I should try that first one again. Jumping around on me, it doesn't quite want to line up perfectly. How frustrating. Smidged it over a little bit. Still looks like it's closer to 200 than anything, so I'm going to stick with that. I don't want to jump all the way down to 150. If I check this first harmonic, I'm definitely over 300, but it's not as perfectly evenly spaced when you use a real voice to do these sorts of things. Okay. Next up would be looking at that roll off, that change in amplitude of the harmonics as you increase the frequency of the components of the voice. So for there, we're looking at amplitude, starting up here at maybe something like 68, and then going to the top of this, which isn't quite where my dot is actually. Looks like about 59, 58. I could go with 58. My next drop would be from there down to the amplitude of the third harmonic, which looks a little bit lower than 48, maybe something like 46. And then my next drop down here would be at the tip of that harmonic. And if I head over, I'm maybe at 36 or 35. Might have kind of wandered up when I drew my line a little bit. But as I look at each of these jumps, and I consider my multiple choice options of drops by 5, drops by 10, or drops by 20, I'm going to go with 10 as being the closest number in those cases. If we were being kind of sciencey, we could do the difference for each one, average the difference across those three differences, use that for our answer, but again, round it off to the nearest 5-ish. That puts me at minus 10. Okay, and then the third question on here is a bit that I didn't talk about at the end of class last time. I was in those last few slides and I kind of ran out of time. There's a general connection between the roll-off and the quality of the voice. Our modal voice quality is our typical, our ideal, and so then that would be that minus 12 dB per octave number. which I would probably, in this multiple choice case, equate with 10 being close enough. We have two other options in here. One is breathy, and you might be intuitively familiar with breathy voice, a voice that's got a little more noise in it. That tends to have a steeper roll-off. The breathiness reduces the amplitude of the higher frequency components. On the flip side from a breathy voice, where you've got a little bit of gap between the vocal fold throughout phonation, letting noise through, making that breathiness, we have sort of extra tightly contracted vocal folds, pulse a vocal fold, vibration as a voice quality. That's sometimes also called glottal fry. And that's actually basically my voice quality. I have this pattern. One thing that pulse voice quality does is reduce the air pressure you need to make phonation happen by a little bit, because you're kind of tightening up the vocal folds in a way. Making a thinner edge that vibrates to give you your frequency. That increases the amplitude of the higher frequency component, so that ends up giving me a shallower roll-off in general. So in the case of the multiple choices I have here, I would probably associate that one with the -5, and I would associate the steeper one with the -20. So bigger drop, larger negative number, steeper, smaller drop, smaller negative number, shallower. Description of the roll off. Okay, so we have a second question with basically all the same stuff in it, but as you can see, that spectrum of the voice looks quite a bit different. We have, again, the fundamental frequency here. Keep doing F1, F0. I'm going to do F1 later. My first harmonic here. My second harmonic here. My third harmonic here. And then after that, I barely have anything sticking out. So I've kind of lost my distinct harmonics. Be hard to pick them out from that just general kind of noise floor that we get in a real spectrum when we make a spectrum of something. So the harmonics have kind of disappeared below that slanting off overall curve of things. That is the noisiness in the voice. So if I take my vertical line here, stick it over on this guy, not too bad. Inching close to 300, so I guess on my multiple choices, I'll go with the highest one I've got available, 250. Something like 275 would probably be better. But for a multiple choice, pick the closest value, get on with your life. Okay, change in amplitude of the harmonics. Again, it looks like we're somewhere around 68 to start. For my second harmonic, looks like I'm down here right around 50. So I've dropped by 18. And then we skip the second harmonic and go on to the third harmonic for another octave doubling. And we seem to be at, maybe 32? Well, 32 would be a convenient number to pick, because that would again be a drop of 18. So among my choices of 5, 10, and 20, I'm going to go with 20 as being closest to 18. And again, that's a steeper roll-off. And in terms of voice quality, we tend to get that steeper roll-off with a breathy voice. And if I kind of swing, that back to my spectrum I have of this speech sound, again, no distinct harmonics above the noise, that breathiness that's in the voice. And we'll talk talk about that more in the next part of this, looking at phonation disorders, because of course one problem you can have with phonation is a difficulty getting actual vibration, periodicity, phonation happening, and what you get as a result in that case is breathiness. So we'll talk about that some more as we move on in this class and start to talk about phonation disorders, like a dysphonia, where you lose that vibratory part of your phonation. All right, me and my vocal fry are going to wrap it up there.